All right. So welcome to our third meeting. Today we're going to talk about linear regression and why it's important, why we need it, and how we actually go about using it. So what is linear regression? You guys are probably familiar with it, and this is going to be kind of a shorter lecture. But it is important to define what we're doing and how to actually use it. So linear regression is a statistical method, and it summarizes the relationship between two continuous variables. We'll talk about what that means, really. The variables that we're talking about, we have two main types, and you guys are familiar with this, but I'll show you why. There's the x variable and the y variable. The x part of the variable is the predictor or a hypothesis or an independent variable. Okay. The y is the response, it's the outcome, and this is dependent. You guys are familiar with this terminology, right? We know what a function is, f of x equals y. We have some function, and the output is y. The input is the x input. That's the predictor, that's the independent variable. That's what can change, right? We can put 5 into this function, we could put 100 into this function, that can change. Y is dependent on this x. So y will change based on what x was. And so we have different functions for this, and this is what functions pretty much are. We have different predictors and variables. Linear regression it uses these ideas in a slightly different way. And so this is just an illustration. I'm sure you guys have probably seen this before, but we have the x-axis and we have the y-axis. The x-axis is, again, our independent variable. This can change. Let's say we input 30, and the output is going to be whatever y is, whatever our equation is. And so in this case, let's just say it's 8. Interesting. Okay, so we have a bunch of data over here, right? We can see we have these dots. And so, for example, we input 60, we observe that the output is 12, let's just say, right here. Now, when we plot this, right, using the scatter plot, we can kind of see that this is a linear relationship. And linear relationship is just a line. It's just a straight line. And so, well, we want to find the best line, or the line of best fit. Which line is going to best fit our data? And this is what linear regression does. It's a pretty powerful technique for linear data, right? We can kind of observe that this data is linear. And so when we have linear data, we can observe that we want to find the best line that can map this data. Basically, we're building a model of what this linear data is. Now, linear regression is limited to linear data, right? So if we have nonlinear, for example, if we have this curve like this, like maybe this is x squared, linear regression is not going to do too well. It's not going to model our data well enough. What it's meant for is, again, linear data. And so when we have this linear relationship, this correlation, sort of one-to-one correlation, linear regression helps us build a model of what we want. And the reason we want this, why do we even want to build a model? Why do we care about linear relationships? Well, okay, we have this data right here. We have all these dots, this data that we have. Let's say we have somebody all the way over here, and let's say this x is age. Okay, it doesn't really make sense because we have negatives, but let's just ignore this part and say it's the age variable. And y could be whatever. Let's say the amount of money you make, let's just say. Let's say, well, we have this data from 10 years old all the way to 60 years old. But what if we have somebody who is 70 years old, who is not in our data set? It's going to be important for us to try to predict what this what the 70-year-old is making. And so we can use our linear model, right? We trained, the technical term is training our model on our original data set. And then we came up with this line of best fit. And what this line of best fit does is it's the best line that models for this linear relationship. And using this line, we can predict that, okay, if you're 7 years old, let's say you're at this point, let's just say. And so this is the power of linear regression, is that it can be both predictive, or you can predict given an input you've never seen before, right? Our data set didn't have a person with 70, but we can predict what they're going to be given the best line, given our original data set. So I'm going to go a little bit into math. It's not too bad, but it's going to be pretty familiar to what you guys know, in that we have our regular equation, y equals mx plus b. All right, well, you guys might be familiar with this. Is just the equation of a line. All right, we have our output y, m is our slope, x is our variable, and b is our y-intercept. Okay, but the way linear regression starts out is by getting a bunch of data. We give it the data. Okay, let's say it looks something like this. We don't know what this m and b are. We don't know what the slope and y-intercept are. And so what the algorithm or the linear regression has to do is learn what m is and learn what b is. The way it does this is by using least squares regression. It sounds a little complicated, but basically what it's doing is, let's say this is our original data point right here. Or sorry, no, this is our original data point. It's going to start off randomly. So it will predict some random line, so a random slope and a random y-intercept. And then it's going to calculate the error. The error, in this case, the way it calculates the error is the distance formula. The way it does that is it calculates where is that point on compared to the data that it's actually at. So the data is actually right here, but the line predicted it should be right here. And so we have some error right here. And the way it calculates that is just the distance formula. It does this for every single point, for every single data point that we have. And then once it comes up with a sort of error, it tries to minimize that. Okay, so it'll calculate the error. So the data, let's say the data point is right here. It calculated it to be right here. The error is going to be small, right? Because if the data point is exactly on the line, the error is 0. But if let's say, okay, we have this line right here, let's just say, and let's say the data point is right here. You guys can see this is pretty far off from the line. And so the distance between that is pretty high. And so the error is going to be higher. And so what it tries to do is minimize this error for every single data point. And we don't have to worry about that, right? We'll look into the code. It does this all automatically for us, but just so you guys can get an understanding of what's going on, it's just trying to minimize the distance between the predicted and the actual. If you guys have any questions, by the way, feel free to interrupt. So the R squared, and again, you guys might be familiar with this, but R squared is a useful value that tells us the proportion, the dependent variable, the y variable, can be predicted from input x. Okay, this is a number from -1 to 1. And so the closer to 1, that means they're positively correlated. what I mean by that is, okay, let's say the line is like this. This is a positive correlation. As our input increases, the output, our prediction is going to increase as well. The closer to zero it is, the inputs are not related, or they're less related. For example, let's say we have some data points like that. It's sort of sideways. This is, or it's sort of random, let's just say. There's not really a clear correlation between the inputs and the outputs. And so our R squared value is going to be pretty low because the correlation between the inputs and outputs is low. Versus in this case where the correlation between the inputs and outputs is pretty high and it's positively correlated. The next value is closer to -1. And this is just negatively correlated. There's still a strong relationship, but it's in the negative direction. For example, something like this. And so what this is saying is as our inputs, the x-axis increases, the output decreases, our prediction decreases. And this is a useful value to know, to understand how accurate is our linear regression model and how well can it predict things. Okay, so we've been we had the equation, right? Y is equal to mx plus b. It takes in the x. The m and b are learned. We don't have to worry about that using the least squares regression. We don't worry about that. But it takes in an input of x and outputs the y. Just like a regular function, right? F of x is equal to y. Same thing, except f of x is mx plus b. But the problem with this is sometimes in the real world, we don't have just one variable. We don't have just one x. We have multiple x's. Let's say we have age, and then maybe we have different types of variables that we've collected, let's just say. Now, we want our model to learn or to understand that these variables exist and try to put that into the model, right? We don't want to just have one variable x. We want multiple variables. And you can do this. Linear regression supports this, basically. And we'll start off with our y, with our prediction. And then it's very similar, but we have multiple mx's, and we still have our plus b, y-intercept. But the reason we have these multiples is because each of these is some variable, it's some feature. Maybe m1, x1 is age. m2, x2 is education level, let's just say. And you can have as many features or variables as you want. Now we'll talk about that. We have to be a little bit careful. But linear regression does support this, and we can have multiple variables. It gets harder to graph though. So you guys are like, if we have this function f of x is equal to y, we know that's a 2D graph, right? We have our x and we have our y. If we have two different variables, so let's say we only have m1 x1 plus m2 x2, that becomes three-dimensional. And so the more variables you have, it becomes pretty much impossible to graph. But we don't really care. We use the R squared metric to basically tell us, okay, how related are these multiple inputs to our outputs? And so we have to be a little bit careful, but I'll show this in the code when we actually implement this stuff. But when we add a lot of different variables, it might artificially increase the R squared score. And so I'll talk about how you actually know if it's artificially increasing it, right? Because the R squared score, the way it's calculated, is it kind of benefits from multiple variables. But it does artificially increase it sometimes. And we'll talk about how do you check if the score is increasing too much. So let's jump in. This was a little bit more theoretical. Let's actually talk about how do you implement this, and it'll bring uh, it'll bring down sort of what we've been talking about into how you could implement this. I'm going to start off with R. Um, the reason this is one of the few times where I prefer R, linear regression, R is built for data science. And so I would encourage you guys to try to mess around with this in R. We'll do this in Python too, but you'll find it's not as powerful. R really supports a lot of features, and so we'll show how that goes. All right, so let me go to my R GUI. This is, again, you might be using RStudio or RGUI, and then we'll go to the Python one later. Remember, you have to change directory to the train and test wherever that is located. And so just like in our first lecture, we want to load in the data set. And so we do read.csv, and then we type in the name of our file. Just to check if it loaded incorrectly, we just do head.csv, and this prints out the first 5 elements. And so we can see that it loaded incorrectly. Okay, so we want to do our linear model. We want to make our linear relationship. We want to check. Okay, well, what is our y? What are we trying to predict? We're trying to predict if they survived or not. What feature, what variable do we want to use to check if they survived or not? We'll start off with just one variable, and then I'll show you how you go on to multiple variables. But let's start off with age, right? Maybe the age is linearly correlated with whether they survived or not. What I mean by that is, let's say maybe there's some correlation between maybe the young survived, whereas the older did not, or maybe the older people survived, more likely to survive. And so let's just build a linear model for just age and if they survived or not. So the first thing is you make some variable name. I'm going to call this reg for regression. You can call it whatever you want. But you're going to set that equal to lm. Okay, LM is short for linear model. And so LM parenthesis, and then the first thing we're going to do is what is our y variable? Our y variable in this case is survived. Right? We want to predict this. This is our dependent variable, the output. And so what we're going to do is access the survived. So we do df. Remember, df is where our data is located. df $, survived. And remember from last time, this is how we access the column. And then we're going to do this little tilde symbol. If you're on Windows, you do Shift, and then it's in the top left. But you do this, it's this little tilde symbol. And then the next thing is what is our x variable? In this case, let's just say we want to do age, this age right here. We just do df $age. All right. And then we're going to do comma, data is equal to df. This data, you have to put it data, and you have to, it's case sensitive, so you have to do data equals. And then df, again, df is where our data is stored. This is a variable name, so it might be different for you. If you put right here, df equals read.csv, if you put that as a different variable name, that'll be different for you. But we press enter. All right. Next, so this is basically R did everything for us. It built our model. Now, how do we access the model? How do we see how well it did? How do we get the R squared value? What we do is summary, parenthesis, reg. And again, reg is whatever variable name you named it, but summary reg. And we get this output. It looks intimidating, but we'll break this down. These residuals are kind of important, but it's a little more complicated. And if you take any statistics class, they'll go over this. But in this case, they're not too important. What is important is, first of all, let's look at our R squared. We'll go to this bottom, multiple R squared and adjusted R squared. Okay. When I was taking stats, they didn't really explain it, so I'm not too sure what the difference is between these two, but it was always told that you look at the multiple R squared. So we'll just go by that and look at what the multiple R squared is. And so we can see that it's 0.005. That's a pretty low number. That's really close to zero. And if you remember, whatever is close to zero means there is not really a linear relationship between the inputs and the outputs. Remember, in this case, the inputs was age and the outputs was survived. And so what this is telling us is that there really isn't a linear relationship between the age and if they survived or not. Now, right here is important, but we'll go to the Python version first, and then we'll come back to this and do more variables. And we'll talk about why this is important. But I'm going to leave you hanging for now on this part of it. So that's how you do linear regression, simple linear regression for only one variable in R. Now let's go to the Python version of it. I'm going to use Colab. Again, if you're using regular Python or Anaconda, that's fine as well. Again, the first thing we want to do is import our data. So again, you have to import, I already did this, but you have to upload the train.csv to the Colab document. And so the first thing is we use pandas to import our data. And then we load in the data. So we would df, again, it could be whatever you want, is equal to pd dot read underscore csv, and then train.csv. And then just to check it loaded in correctly, we do print df.head, and this prints in the first 5 elements, just like last time. Now let's do the same thing. Let's do linear regression for age compared to if they survived or not. To do linear regression, we're going to use sklearn. This is a library. If you're using Anaconda, this should already be installed, or Colab. If you're using Python, the regular install, let me know if you're having trouble installing that. But we're going to do from sklearn dot linear model, linear underscore model, import linear regression. I'm going to run that. Okay, so, but there's a problem with the Python version. In R, it worked fine, right? We didn't really have to do much. That's the power of R. In Python, it's a little bit more difficult. We're gonna have to go through a little bit more steps. And the reason for this is let's print out let's print out the unique values of age. Right? We want to access, okay, df age dot unique. And this prints out the unique values of age. And so we can see we get 22, we get a bunch of values. And these are of people's age. But you will notice something. We have NaN. Okay, this is not good. What NaN means is null or none. Basically, it doesn't exist. So when people were gathering the Titanic data, they found some guy, or let's say person 20. Person 20 doesn't have an age. They couldn't find it. And so what they did is put it as none. We don't know what the age is. And this is a problem. Python can't handle for null values. R could. R did everything for us. But we need to get rid of this NaN. And this is a common problem you'll find in data science, machine learning, that sometimes your data set is empty. Sometimes some values are null. They don't exist. And so the common approach, how do we fix this? We want to do linear regression, but how do we fix this null value? the common approach is to fill all of these null values with the median, right? I'm sure you guys are all familiar with the median. We can access what the median is. And let's actually print that out. df age dot median. And we get 28. Okay, what we want to do is fill every single null value with this 28 value. And what this does is it allows us to do the linear regression without changing much. It doesn't change our data set too much while allowing us to actually do it. All right, so how do we change our, how do we fill every single null value with the median? And the way we do that is by doing df dot loc. I'm going to refer to my notes here, but no, sorry. So we're going to do df of age. And this accesses the age column. I want to set that equal to df of age dot fill na. All right, and this is a function. So what fill na does is fills in all the null values. But what do we fill it in with? We want to fill it in with the median. And so I'll just copy this and put it in this. And so what this is doing is it's filling every single null value with 28. Let's run this. Let's print out the unique values of age right now. And you can see there is no null value, right? Null was right here, but we see all the null values are now 28. And so Python will be able to run this now for us. All right, so what's the next thing we want to do? Let's declare our two variables, our y and our x. All right, so I'll do x train. Again, this could be whatever you want, is equal to df of survive, or df of age. This is our x variable. Then our y variable is going to be our survived. All right. Now we have another problem though. For technical reasons, we need to reshape this data. Let me actually go through and I'll show you the error message that you'll get. But we need to do one more step before our linear regression. But let's just do our linear regression now and I'll show you the error that you get. And so the way we do our linear regression is by doing reg, you can call that whatever you want, is equal to linear regression, parentheses, right? And then we're going to do reg dot fit the x train, the x variable, and the y train. Now, when I run this, I'm going to get an error. All right. The error, reshape your data using, all right, basically the error is saying expected 2D array got 1D array instead. This is a technical reason. Python, the way they programmed it, they expect a two-dimensional array. We need to reshape this data to be two-dimensional. Right now, it's a 1D array. It's not too important to understand this. It's just for technical reasons we have to do this. But the way if you ever get that error, and this is a common error in machine learning and data science, the way you do that is by doing, again, x train is equal to x train. This is kind of the easiest way. And it's not too important to understand why, but it's okay, like x train dot 2 underscore numpy dot reshape -1 by 1. Okay. This is the same thing as just adding a column right here, right? We could do that actually. and this would work fine. This part wouldn't throw an error. But I want to show you guys the correct way of doing it because sometimes it's not as simple as just adding these two brackets at the end. And so just to show you the correct way, this is kind of the correct way to do it. And so we have that, but we also need to do it for the Y train. So Y train will be equal to Y train dot to numpy dot reshape -1 by 1. What -1 means is let numpy decide what the shape is going to be. But then add an extra column, add an extra dimension to it. It's just for technical reasons. Don't be too concerned with that part, but we'll run that. And then now we call it, and we don't get any errors. Now, how do we access the R squared? The way we access R squared is by doing print reg.score parenthesis again, and then again you need to pass in X train and Y train. And when we do that, we get 0.0004. This is pretty similar to the R, right? Let me share the R, what we got with the R. We got 0.005, 0.004. It's pretty close to what we got, right? It's again, very close to 0. And what this is telling us is that there's no relationship. There's no very little linear relationship between the age and the survived. All right. Now let's move on to a little bit more, not complicated, but we can see age and survive don't really have a linear relationship. But let's test it for more variables. What if we want to test age? And because we have a lot of features, we have a lot of variables, right? If we can print out the number of variables we have. df.columns, we have all these different variables. P class, name, sex, age, number of siblings. And we want our linear model to maybe, if we add all these different features, variables, maybe our linear model will do better because as you can see, the linear model is not doing well. It's basically telling us there's no relationship. And so it's pretty much useless right now. But let's go to the R version. Is there any questions, by the way? All right. So again, we want to do multiple variables now. And okay, what we're going to do is, again, reg is equal to lm. df of our y variable, df of survived, and then our little tilde symbol. Again, this is exactly what we did right here. And then, okay, let's look at different features that we'll use. Let's say we again want age. Let's just put in age, df of age. Okay, but how do I add on an additional feature, an additional variable? The way we do that is by doing the plus symbol. Plus, plus df of, let's say we want sex. Df, maybe sex has to do with if they're male or female. That has to do with if they survived or not. And so now this will be a combination, a linear regression model of both age and sex, trying to predict survived. We don't have to stop here. We can add as many as we want. df of, let's say, P class. And this is the class that we're in, like first, second, or third class of the ship. This kind of is dependent on how much money you have. All right. Now, P class, maybe the fare matters, how much you paid for it. df of fare. And again, this is all in the number of columns that we have. And maybe the number of siblings that you have matters. So plus sib sp. And then, well, let's do all this for now. And then again, we're going to put comma, data is equal to df, which is where our data is located. So again, what we're doing is we have our y variable right here, what we want to predict. And then we have all of our x variables. And we can have a lot of them, as you guys can see. Before we only had one, we only had age. But now we have many of them. And we press enter. And then again, we're going to do summary of REG. And we get this, again, this intimidating text, but we'll break it down again. And we'll see something kind of cool. We go to our multiple R squared, we get 0.4. That's higher than we had before, right? Before it was 0.004, very close to zero. 0.4 is kind of promising. It tells us that there's kind of a linear relationship. It's not too strong of a linear relationship, but it exists, unlike before where it just didn't exist at all. And basically what this is telling us is that there is kind of a linear relationship between all of these features. Now, let me break this part down. I left you hanging before. What exactly is all of this? We can see we have all of our little variables, age and sex and P class. But what do all of these mean? It looks intimidating. And if you take a stats class, they'll explain this a little bit more in depth. But what this is telling us is what our intercept and our slopes are, as well as the significance of each variable. Let me break that down. I kind of went through a lot there. We have our intercept right here, our first row, intercept. And then we have 1.3. This is our intercept, our y-intercept, right? This is the plus b at the end of the y equals mx plus b. That b is 1.36 in this case. Now let's look at the df of h and what this is. This negative 0.064, that's the slope. That's the m. mx plus b, that's the m. That's our slope for h. Remember, we have multiple slopes because we have multiple variables. But all of these is our slopes. This is the slope of sex. This is the slope of P class, and etc. Now, these aren't too important right now, but this is, for right now, this is important. This column right here. What this is telling us, this is important because this tells us how significant is our variable. Okay, what does that mean? Well, sometimes our variable, what we're using to predict if they survived or not, has nothing to do with if they survived or not. In any case, it's not significantly predicting the output. That's the way we can tell if it's significant or not is by this is called a p-value. And if you take a statistics class, they'll go into this a little bit more. But you guys can see this really low. This is almost close to zero. The closer to zero this is, the more significant the variable is. And so R kind of tells you what is significant, what isn't significant. We can see here we have these like stars, triple stars right here, right? R is telling you that these variables are very significant. These variables are important. What isn't important, what's not significant, is fair. How do I know that? Because there's no stars here. And the p-value, right, the 0.42 is very high. The way it's sort of determined is if it's higher than 0.1 or 0.05, it's too high and it's not significant enough. 0.42 is way higher than that. And so R is telling you this is not significant at all. And so what we should do is run this model again, but without the fair variable. And even though we'll see what happens actually. So let's go back to this. And then let's delete df of fair because that's not significant. And we'll run that and we get the summary. You're going to see that the R squared went down a little bit. Not much, but it went down a little bit. That's okay because I remember I told you that R squared, it sort of makes it beneficial to have more variables. But that's not the case. We only want significant variables. And as you guys can see, every single variable here is now significant. The age, the sex, the P class, the number of siblings. And so this is now a significant model, or these variables are significantly contributing to if they survived or not. And again, we look at our R squared. This is sort of the value of if our model is good or not. And when we look at our R squared, we get 0.4, 0.399. It's not bad. It's telling us that there is some sort of relationship. And this is it for R. This is pretty much the basics for the R part of it. I'll quickly go over how we do this in Python. It's again a little different, a little bit more, not difficult, but a little bit more steps. R is built for data science. And so remember, we'll go by the number of, we'll do the same number of significant variables because Python doesn't, there is a way to get the significance of each variable, but it's a little bit more difficult. And so I recommend just doing it in R. But let's only use the significant variables that we have. And so the way we're going to do that is by, again, we're going to have, we're going to set the columns that we want equal to the age. Age was one of those variables. To sex, to the number of siblings, and to the P class. These were all the significant variables that we had. Remember, fair wasn't significant at all. But again, there's another problem with Python, is that the sex is a categorical variable. And let's actually print out what the unique values in sex are. It's male and female. Python can't handle for male or female. Python, or the way they wrote it, it only handles for integers, for numeric values. And so what we have to do is convert male, female to 0 and 1. The way we do that is, the way we're going to do df dot loc, and this locates, and then bracket df of sex is equal to male. All right. What this is going to do is check if the sex is equal to male, and then it's going to locate all the values where sex is equal to male. What we have to do next is comma the variable name sex. And then what we have to do is set this equal to 0. And basically what this entire line does is wherever there is a male, wherever sex equals male, it's now going to be equal to 0. Let's do the same thing, but for female. And then we'll set that equal to 1. And let's run that. Now let's see what our unique values are. It's now 0 and 1. In this case, it was male and female, but now it's 0 and 1, where Python can actually handle for this. All right. Now we need to, again, have our X train. This is going to be a little bit different. It's going to be equal to df bracket columns. Columns is age, sex, number of siblings, and P class. What this is doing is getting all these columns over here. Now all of these columns are now going to be equal to X train. Y train is going to be the same way. Y train is equal to df of only survived. That's our Y variable. Now again, remember Python was a little weird. It needs it to be a two-dimensional array, right? What we did right here. In this case, X train is two-dimensional. Because we have multiple variables, X train already becomes two-dimensional. And so we don't have to worry about reshaping X train. Y train is still not two-dimensional, so we do have to retrain that. And so we'll just do the same thing. Y train is equal to Y train dot 2 numpy dot reshape -1 to 1. Again, this is just for technical reasons, so it doesn't really matter too much. All right, finally, we're going to get to now we can get to our regression. And we'll do reg is equal to linear regression, and then reg dot fit our X train and our Y train. And again, we had no errors, so it worked. And now let's print out the R squared. So we'll do reg dot score our X train and our Y train. And we see we get 0.39. Very similar, or almost exactly similar to what we got in the R part. And so this is it. This is how linear regression works, how we implement it, how we can use it. And that's it. If you guys have any questions, I'm going to stick around. But next week, we'll talk about logistic regression, which is a little bit different, similar to linear regression. But that's it for me. If you guys have any questions, I'll stick around. And thank you for coming.